This is a very short chapter, all right, and let me say that in your textbook, chapter 9 is about normal length, but we are only covering a very small portion of it, okay? And we're going to get a lot of review today, okay, on topics from chapter 8. And let's just think about what we did in chapter 8. Our big focus was on these two bullet points. Drawing out Lewis structures and looking at what's called the Vesper model. Included within Vesper, that means shape, bond angle. Maybe they could also ask you, is the molecule polar or non-polar? Okay? But in order to complete what your textbook calls the localized electron model, which basically just means a complete description of a compound, you would need to draw it, predict its shape, and there is a third part here that we're going to talk about today on a topic called hybridization. Okay? Now, I want to tell you that on my test and on the AP exam, there is a very, very small amount of hybridization that you're responsible for knowing. Okay? I could actually cover what you need to know in probably about 5 or 10 minutes. I don't feel right in having you just learn that, so I'm going to tell you a little bit of the background about what hybridization really is and what it means. But please be assured, on the AP exam, on my test, you're probably not going to be asked to explain or draw out any of these background situations. Okay? I will make sure that as I'm talking today, I will call your attention to something that you will be required to do on a test. So let's just start off. What does this word hybrid mean? And you hybrid anything, a hybrid car. A combination, okay? A meshing of two concepts into one thing. Okay, so for example, a hybrid car, you're meshing what with what? Gas and electric, okay, into one car. Well, when we talk about hybridization in chemistry, what are we blending together? We are blending electron orbitals together, okay? We're actually going to be blending their shapes together, okay? And we're going to start with a very simple example. We're going to start with this molecule methane. Okay? And I want you to tell me first, how many valence electrons does carbon contain? 4. Okay, I'm going to draw them out. S, B. Okay. Let's review a little bit here. Anytime you draw a Lewis structure and you draw a line like that, what does that line represent? Okay, a bond. What kind of bond? A single bond. Okay. What is physically in this space? 2 electrons. They're being shared. Shared, meaning one electron is coming from carbon and the other one is coming from hydrogen. Okay? Carbon is contributing 1 in each of these 4 slots, and the other is coming from hydrogen. I want you to look at how I've drawn these electrons out. The way that this is drawn out here, this is called an orbital notation, it looks to me like these 2 electrons are already paired up, so they're kind of off the market. When the electrons are drawn out like this, it looks to me like carbon can only bond with 2 things. But we know that that's not true. We know that it can bond with 4. So the first part of this hybridization story is that electrons can move wherever they are needed. It moves over there. Okay? Doesn't it now look like carbon can bond to 4 things? Yeah. Okay? The gist is, when you have a molecule like this, electrons are not locked in their places. They can move wherever they're needed. Okay. Here's my second question to you. All right? Agree or disagree? These 4 bonds are identical. Agree or disagree? Agree. I would agree. Okay. Andrew, would you close the door on Mr. Greeny's class over there? Thank you. Yes, they are all identical. Okay. Well, that's great, but there's a problem here because these 4 orbitals here are not identical. Okay. Maybe it was last chapter, maybe it was 2 chapters ago, I'm not sure. We looked at the shapes of different orbitals. And we saw that an orbital in an s sublevel has a spherical shape. And orbitals within a p sublevel have, this is called a dumbbell shape. Do those 4 shapes look identical to you? No, they don't. Hold on. You just told me correctly, by the way, that these 4 bonds are identical. Identical in length, strength, shape, everything. But this is where these electrons are coming from, and they're not identical, and they have to be. Ladies and gentlemen, this is the essence of hybridization. What are we meshing together? These shapes. We're going to mush them together so that we get 4 identical shapes. Not identical, mush them together, you get these sort of mushroom shapes. Now they are identical. Okay? So what has been hybridized? The orbitals have been hybridized. Okay? Here is what you will be responsible for on a test question. I will give you, maybe it's multiple choice question, maybe it's free response. You look at a Lewis structure and I would ask you, what is the hybridization around that carbon? Here's what you would say. Ask yourself how many sides are occupied. Okay? When we first started talking about shapes in chapter 8, I asked you that question a lot. If you could imagine a box around this central atom, how many sides are occupied with something? 4. 4. So, this molecule has sp3 hybridization because I hybridized 4 orbitals. 1 s and 3 of the p orbitals. Okay? That is what you will be expected to do. Is to look at a central atom or any atom and tell what is its hybridization. Okay? Right? This is a tetrahedral shape. Let me see if you remember something. Okay, here's tetrahedral. Do you remember the bond angle? 109.5. Very good. Now, okay, this is just another way to look at this. Okay, not only do S's and P orbitals have different shapes, they also have different energy contents, and that's a problem. Again, these need to be identical in every way. They have to have all the same energy content. How do you accomplish that? By hybridizing them together, mushing them together. Now, I'm going to draw some other examples on the board here. I'm going to draw ammonia. And down here, I'm going to draw water. Okay? I want you to look at those 3 structures on the board. Besides the fact that hydrogen is the terminal atom in all three examples. What do these central atoms have in common? Look at it for a second. Okay, all of them have four sides occupied by something, okay? Not necessarily all of them have four shared pairs, but all of them have four sides occupied. And ladies and gentlemen, that means all of these examples are also sp3 hybridized. Okay? Doesn't matter if it's a lone pair or a shared pair. All three of these examples have four hybridized bonds, I guess you would say. Yep.
No, I'm thinking
Okay. Okay. So let's just review for a second. This is good review from chapter 8. This one is tetrahedral in shape. What's ammonia? Trigonal pyramidal. Okay. What's the bond angle here? Slightly less than 109.5. Okay. What's the shape here? Bent. Okay. How would you describe the bond angle? Also slightly less than 109.5. Even though there are lone pairs here and here, and it looks to us like there's nothing there, there is a hybridized orbital right here and right here. There are 1, 2, 3, 4 of them. Okay? All of these examples are sp3. All right. Folks, in this example, I don't want you to think about necessarily yet this entire molecule. I want you to focus in on just that carbon. Okay? And tell me one more time, carbon has how many valence electrons? 4. To do. Okay? Can you please tell me that carbon that I have circled, remembering that shape-wise a multiple bond is treated like a single bond, how many sides are occupied? 3. So how many identical shapes do I need? 3, not 4 this time, just 3. And you might look at this and say, well, these 3 are identical. Why don't we just use these? Well, that would be nice, but there's no scientist that's doing this. This occurs in nature, and what occurs in nature is that one, and that one get used. Okay? So, that carbon, ladies and gentlemen, is not sp3 hybridized. It's sp2 hybridized. And I'm not forgetting about that extra electron. This guy, this extra one, does not just float off into space. It has a role. I'll get to it in a second. Okay? Well, a little bit. Do you see the trigonal planar shape here? Okay? Just like this. What is the bond angle? Do you remember? 120. Okay. What does the word planar mean? Flat, on a plane, flat. Okay, good. So let's talk about that extra electron. What is it doing? Okay, there are your 3 hybridized orbitals. There are the 3 blended shapes. And this shows you that extra orbital that's not hybridized. It's not the same as the others. So what is it doing? Well, let's look at this. First things first, guys, I want you to focus in on these green areas only. For the moment, I want you to ignore the blue. Do you see, if we imagine the carbon right in the center here, do you see that trigonal planar shape? Can you see it? Okay. here's what that extra electron is doing. It's being represented by this blue piece. And it has a dumbbell shape. My understanding is the electron is basically doing a figure 8. But here's this is an important word on this slide, right here. Perpendicular. Okay? Anytime you have an extra electron orbital that's not being hybridized, it's going to be perpendicular to the rest of the structure. Okay? This guy is orbiting, or figurating, whatever, above and below that plane. Okay, now, I'm going to complete this drawing just a little bit to help you get your bearings a bit more. Okay, if you look at these green pieces here, again, there's that trigonal planar shape. Okay. Oh, thank you. Okay. What's in this blue piece right here? What is that? Okay, that extra electron is doing like a figure 8 here. Okay, well guys, if you recall, a couple of slides back, the whole structure here looked like this. Okay. This carbon had an extra electron. What do you think if we did the same kind of thing for this one? Would it have an extra electron? Yes, it would. And here it is. Okay. Ladies and gentlemen, when you get a pair of electrons that are not hybridized near each other, there's a force that exists between them. That's what these little dashed lines are representing. Okay? It's called a pi bond. Okay? There's two types of covalent bonds, a sigma bond and a pi bond. Let's start with the easy one. A sigma bond is essentially a single bond. That's easy to remember. Sigma, single. Sigma, single. The pi bond, well, first, the sigma bond, guys, comes from hybridized orbitals. The green parts, these are the sigma bonds. Okay? When you have a pair of extra electrons bouncing around, they form a pi bond. So, let me just erase this for a second. Okay? Here's what you're going to have to answer about sigma and pi. Probably multiple choice. I want you to look at this structure. I know I erased that second bond. I'll put it back in a second. How many sigma bonds total are in that drawing? 5. 1, 2, 3, 4, 5. Okay? Remember, a sigma bond is just where the hybridized orbitals are. Okay? There are 5. Let me put that double bond back. Okay? I want to make sure that this is absolutely crystal clear because this is a big misconception that people have. A double bond is not a pi bond. A double bond is one sigma bond, a little sigma symbol, and one pi bond. What do you think a triple bond would be? Yeah, one sigma and 2 pi bonds. Okay, I'll show you an example of that in just a second. So, again, here's what a question might look like on a test. Here's a drawing. How many total sigma bonds are there? 5. How many total pi bonds are there? 1. Yes.
So every single bond is always a single bond.
Correct. Covalent, yes. So I'm going to draw something up here that's like totally ridiculous, using elements that don't exist. Like X triple bonded to Y, single bonded to Q, H, double bond to J, H. Okay? Look at what I've drawn here in pink. Look at the whole structure. Make sure that looks connected. How many total sigma bonds do you see? 5. 1, 2, 3, 4, 5. How many total pi bonds do you see? 3. 1, 2, 3. Okay? Now, please do not be intimidated by this drawing. I am never going to ask you to draw something like this. It's just to give you a visual representation of what this molecule really looks like in 3 dimensions. Okay? The pink spheres represent hydrogen atoms. Here's your carbon. What are the green parts representing? Wait, not sp2. I mean, it is sp2 hybridized, but what is each of these green pieces?
Sigma bond.
A sigma bond. Are sigma bonds hybridized, yes or no?
Yes.
Yes. What is physically in this blue area? An extra electron. Here's another one. What are we representing with these dashed lines here? Pi bond. Okay.
Is there one pi bond or one pi bond?
There's one pi bond. I know this looks kind of confusing. This and this together represent one pi bond. And guys, keep in mind, we talked about this before, whether ionic or covalent doesn't matter. A bond is not something that you can touch. It's a force that exists between two things. It's just a force. Okay, let's move to one final example here. Okay, tell me. How many sides of carbon are occupied by something? Okay? So now I need only 2 blended orbitals. So this is just sp. You don't have to write the 1. It's just sp. Hybridized. Do you see that there are now 2 extra electrons that'll be bouncing around? What do you think they're going to do? Create 2 pi bonds. Look at that structure. Don't you see 2 pi bonds in there?
Yes.
Okay, let me pull up a picture of this. Folks, this is what carbon dioxide looks like.
Yo.
I'm not going to ask you to draw this.
You asked us like identify what that is.
Probably not. Okay, but it's my wish that you understand what's going on here. Again, all you are responsible for is identifying what is the hybridization. Well, I could have taught you that in 5 minutes. I want you to understand at least kind of what's happening here. Okay? Here's a sigma bond. Here's a sigma bond, here's a sigma bond. Here's one pi bond. Here's another. They are perpendicular to each other. Okay? Please tell me, in this CO2 structure, how many total sigma bonds are there?
2.
How many pi? 2. 2 and 2. What every example we've done so far, I've been asking you the hybridization around a central atom. I could ask you any atom that I want, though. What is the hybridization around one of the oxygens? How many sides are occupied? 3. So, sp2. Remember, a multiple bond counts like a single bond when you're thinking about sides. Okay? Now, Evan asked the question, what about hybridization when you get to some of the extended shapes, like when there are 5 sides occupied, 6 sides occupied, like octahedral, some of those extended shapes? This is a change from last year to this year. Okay? The chemistry community is kind of in debate as to whether hybridization exists at all in those upper shapes, those extended shapes. They are not in agreement on whether it even exists, so the AP exam the College Board took it out. Okay? Like, for example, something that has 5 sides occupied, you would say is S, P1, P2, sp3D, hybridized. And then if you have like octahedral with 6, it was S, P3, D2. Okay? But again, they're not convinced that that even exists. So you are responsible for hybridization on the basic shapes only, like the Chem 1 shapes. Ladies and gentlemen, this is practice, and this is what I want you to do. Okay? These are some of the simple shapes. Okay? I want you, for each of these, this is excellent review, I want you to draw it, tell me the shape, the bond angle, the polarity, and the hybridization around that central atom. That is a complete picture. Go. hopefully this is getting your brain a little bit back in gear. Okay? Doing this sort of exercise is my way of saying to you that this test that we're taking next week, yes, it's chapters 8 and 9, but do you see what a tiny little sliver chapter 9 is? It's basically a chapter 8 test with a little bit from chapter 9, but not much. Okay? So let's wrap this up. Okay? What's on this slide is review as well. We have already talked about resonance. Okay? So I'm going to draw this example out. Nitrate. Okay. Does that molecule have resonance? Yes or no? Probably, since it's on a resonance slide. Okay. How many total structures could you draw? 3. Just move the double bond around, or that second bond around. Okay. Why is this slide in this chapter? Because we now have some better vocabulary that can help us describe resonance. Okay? Now, first things first, let me just remind you a little tip about resonance structures. Let's say you are given the molecule NO3- and the question just asks, what is its shape? That's it. Nothing else. What are you going to say? Trigonal planar. Okay? Was the concept of resonance a part of your thought process at all? No. Okay? If they are asking you just a shape or what's the bond angle, that has nothing to do with resonance. You don't need to draw out all 3 structures if the question has nothing to do with resonance. But what if the question asked you between these 2, let me draw this other one out. Okay, what if the question asked you NO2- versus NO3-, which has the shorter bond length? That is a resonance issue. And again, don't shoot the messenger. If it's a question of resonance, you must draw out all the structures. How many total Lewis structures would you have to draw for this question? 5. Okay? How would you describe the average bond length in NO2? Okay? 1.5 is the right thought process. It is basically the length of a bond and a half, but you can't say that. Between the length of a single and double bond. Well, so is this one. Which one has the shorter average bond length? Incorrect. It's NO2. Okay? So this is like a bond and a half. What's this one? Like a bond and a third. Okay? Nope. Hold on. But you can't say that. So both of these, you would have to draw everything out. You'd say, although they both have an average bond length between a single and double, the average bond length of nitrite is closer to that of a double bond, which is shorter. Okay? Longer, shorter. Now, here's why I put it in this chapter. How do you say in an electron pair that's jumping around? You can't say that. You can't call them Mexican jumping beans. Okay, you have some options. What could you call them? Okay, you could call them resonating electrons. What else? Okay, what does the word delocalized mean? Not localized. Okay, well, what does that mean? Foreign. No, wrong. Can localized means something that doesn't change its location. Delocalized means it does. It can move around. And if you want to be really fancy, people, which you should, you would call it a resonating pi bond. Now that you know what that word means, you should use it. Okay? Ladies and gentlemen, sigma bonds cannot move around. They're always localized. Quick review. How many sigma bonds are in this drawing right here? 3. How many pi? 1. Very good. Okay. I want you all to be aware, much like our last test, where a chunk of the free response was those 2-sentence maximum questions, where you have to be really specific and use certain words and phrases. There's more of that in this one. Okay? Might I recommend, before our next test, that some of you might want to come and go over your most recent test? Okay? Just a thought. Putting it out there. This is the last topic. It's super quick. Okay? This topic is going to seem extremely detached from what we have been talking about, and it is somewhat, but it's in Chapter 9, so we're covering it. Okay? Para and diamagnetism. Okay? It's very much a physics concept, so we're just going to barely scratch the surface here. If you would like more info, go ask a physics teacher. Okay? Here's the thing. Whether you know it or not, ladies and gentlemen, some elements out in nature are naturally magnetic. Can you give me an element that is naturally magnetic? Iron. Yeah, your magnetic refrigerator is magnetic because it's made of steel, which is mostly iron. Okay? There are elements that while you dig them up out of the ground, they might not be magnetic just out of the ground, but if you bring them near a magnetic field, you can induce them to be magnetic. Those are elements that are called paramagnetic. And then there are some elements that you could bring them near a magnetic field and nothing happens to them, okay? Or they do not become magnetic. Those are called diamagnetic elements. And guys, whether something is magnetic or not depends all upon unpaired electrons. So, look at your periodic table, please, or the one on the wall. Look at where magnesium is. How many valence electrons does magnesium have? 2. Are those electrons paired up?
Yes.
Okay. Well, those are just its valence electrons. What about all of its core electrons? All paired up. That means no matter what you do to magnesium, it is not capable of being magnetic. So this is a diamagnetic element. How about bromine? Diabetic. No.
Yes.
No.
I don't know what yes and no means.
It is paramagnetic.
Okay.
Do you know like whether it's either on or
No.
okay.
You can't go with
Oh,
that.
I see why.
Okay? That has an unpaired electron. Just one. But one is enough. That is a paramagnetic element.
Does that determine how strong the magnet
I don't know. Someone asked me that one time, like, if it has more unpaired, does that make it more magnetic? I want to say yes, but I'm not 100% sure about that. Cadmium. Transition metals, it's right underneath zinc.
They look expensive.
What do you think?
Oh, I see.
All paired up. Diamagnetic. How about nitrogen? Krypton.
Diamagnetic.
Manganese.
Wait, what about like iron? Oh wait, you don't know because it's like you don't know how many grams.
Doesn't matter. Ladies and gentlemen, I chose manganese for a very specific reason. How many valence electrons does manganese have? 2. And they're paired up, right? Okay, so is this a diamagnetic element? But these are core electrons. Doesn't matter. I'm trying to trick you. Okay? It doesn't matter. What I'm saying is, that backfired, didn't it? Okay? What I'm trying to say is, it doesn't matter if it's a valence electron or a core electron. If any electron is unpaired, it's paramagnetic. Okay? All right. That's it. That is all of chapter 9.